So, a very good morning to all the esteemed participants and resource person. So, we are going to start our fourth session, day two, and we have with us Mr. Karthik Kameswaran. He is the expert for session four. So, let me take the privilege of introducing our resource person to the participants. So, Mr. Karthik Kameswaran. He is working as a program manager in EBTS. Uh, he is a Bachelor of Engineering in Information Technology from Mumbai University. His expertise includes IT program and delivery management, digital transformation, tech strategy, quantum computing, and he has more than 17 years of experience. He has managed a key project that helped the company to beg CNBC NESCOM IT User Award in 2009. He was awarded IT Appreciate Quarterly Performance Award in 2007. He has also received Team Award for Quarterly Performance in 2007. So I welcome the resource person again, and I request uh, Mr. Kameswaran to deliver his talk. Sir, please.
Thank you, sir. Thank you for the introduction. Let me quickly begin with the session. I'm assuming that the audience is relatively new to quantum computing. That's an assumption that I've taken, and I'll be having a short talk on the basics of hardware. So we'll be referring the regular computers as classical computers and quantum computers as them. So that's a terminology that I'll be using. The goal of this session is basically to be able to introduce the very foundational fundamentals of the quantum hardware. I understand that some of the sessions you have already covered. You would have covered on the quantum gates. You would have covered on what are the qubits. So those are something that you would have covered. I'm here to help you bridge what is the quantum hardware which is actually powering these gates, and also be able to bring out that variety and appreciate that variety, the scientific challenges, the technical challenges that come along with them. You can feel free to ask any questions at the end of every slide. So any questions, please shoot out. Uh, so uh, so I hope we can have a great interaction together. So uh, we are all aware of classical hardware. Okay, so we know what are the major components. When we talk of the classical hardware, we know that the CPU is very good at general purpose computing, the variety of tasks that it performs, and it's limited by the parallelism that it can perform. So some of the co-processors have evolved, like Xeon Phi, or NVIDIA GPUs. So there are so many co-processors that are available, and some of the things that you are already aware of are the graphics cards that you use in your computers. That helps in a better graphics, that helps in computing, GPU computing. So these are co-processors, and FPGA is another special type of co-processor, in the sense that it can act either as a co-processor or a communication component or a mixture of both. And this is because it's programmable. The obviously that being a co-processor is one of the forms that it can be leveraged. Similar to this FPGA and GPU, our quantum computer is essentially a co-processor in our ecosystem. While there are computers which define, saying that, hey, take this quantum computer, essentially what they are giving is a quantum computer, and along with a classical computing network subsystems, which together appears as a single computer to you. So quantum computer in essence is only a co-processor in today's ecosystem of being able to leverage them as computing power. It's still a co-processor. Okay, and it cannot exist in standalone. We'll see a bit about that later. Uh, just to give you a background of the IBM architecture, I mean, our classical computers, how it evolved, because we can relate to how the quantum computer is evolving, and we can understand that the IBM architecture typically had this. Open architecture that they started in early 1970s, and it kind of evolved. While the communication started evolving between the computers, there was network issues. The network was not as robust as it is today, so obviously we had a lot of errors in the network. And the network obviously required parity bits and so on and so forth. And also we know that Intel employed something called as error checks within their microprocessor the day when they introduced those branch prediction on out of order computing in their early 1990s. They actually introduced a lot of error checks within their microcode. So essentially the microcode is the one that you have within the chip. So today, the quantum computers are in exactly a similar state where there is a lot of errors that need to be tackled, and there are a lot of error rates. And these come inherently because of the probabilistic nature of the computing and the quantum effects within the materials, and the noise and the whole setup that we have for the quantum computers. And this results in a lot of errors, and that's why what we do is in quantum computing, essentially we run many loops, and we take the highest probabilistic outcome. Every run need not result in the same outcome, so there is this concept of running it in loops and finding out the most probabilistic results, and the rest are considered as outliers or errors. So these outliers must be made as minimal as possible. And if you really look at the whole ecosystem, the interconnects between the various components are essential. I mean, any computer that you see is actually having so many components, and interconnect between all of them is so critical. And the critical components, while we focus a lot of these for the critical components, the interconnect also is essential, because that is exactly how the quantum computer is going to get connected to the host GPU. The interconnect between the quantum units, between the qubits. So those are something which are essential. So these links actually help an appropriate communication between the components, and they are actually very difficult to control in a quantum computer, because there are noise effects that can affect these interconnect. While in a classical chip, the interconnects today, we have a very stable connection interconnect, because it doesn't get it doesn't get impacted by your radio signals, or it doesn't impacted by the temperatures so easily. Whereas in the 1950s and 60s and 70s, when the computers were evolving, this was really a concern at that time, and quantum computers are probably in a similar state today. You will see that if we look at the quantum computer, the basics of how they are built, will come to that part where we are talking about the building of each qubit. When we are talking about that, you will understand that there are certain thermal noise, there are external magnetic electromagnetic noise that can interfere, and these interferences will actually impact the whole computing. And so the susceptibility to errors is something that we need to take care of in the interconnect also. So the logical block, if you look at the logical blocks of a quantum computer, they are very similar to what you will see in a modern computer, I mean the classical computer. But the physical blocks are way different, and we are going to talk a little bit about the physical components today. Any questions in this? Okay, let me move on. So how do we get an access to to the quantum computer. We have everyone talking about the quantum computer being accessible. There are so many quantum computers that have been built. In theory, if you see, there are about 300 odd quantum computers that have been built. The working models that we are talking about. While those 300 computers are available, are they accessible to everyone? Probably no. It has been limited to research, a lot within the universities and a lot within organizations for their own R&D, and people are trying to see if it really works for a wide range of use cases. Some of them are useful and some of them are not. So you see, companies like IBM, they have started offering quantum computing as a service. I'm pretty sure a lot of you would have gone through that, IBM offering and seen the Qiskit as one of the ways to do quantum computing. So these Qiskit is essentially what we call either a SDK or a scripting interface to the quantum computing, and it's similar to a cloud-based SaaS service that you find like an AWS or a Google Cloud service. Similar to that, you have IBM Quantum Computing as a service, and the majority of the users actually fall in this category of utilizing this service. You really don't need to know the quantum hardware which is powering. I mean, for most of the people who are using this IBM quantum computing, they really do not know what is the hardware which is powering their service. So they do have something called as a simulator, and they do have something called as an actual quantum computer being available to run the jobs. So people are very much unaware of what's going behind, but IBM has done a fantastic job in packaging a computing interface for the people to consume. And the next part is actually the companies. There are companies who buy themselves pre-built quantum computer. Like there is a company called D-Wave, so which sells quantum computers, and a lot of companies have bought that to explore, to do R&D, and this is expensive. I mean, it's not really easy. It's pretty expensive, but it gives a complete control of the computing power and whatever integration tools are available to them, so they can integrate it with their existing software, try to do certain experiments and run and see if it's useful for solving any of the software problems they are having. For utilizing these kind of computers, you would essentially need a good knowledge of tools and hardware to get the fastest return on investment, and you essentially need to put out a lot of you know uh, integration, and so that you can leverage it with your existing system. And the third, which is obviously to do build a ground up quantum computer. This is extremely, as with any approach, any classical computers also, it usually gives great flexibility to build whatever that you want, and you can have your own custom integration with your own software tools. But it's obviously the most expensive approach because it really takes time. It really takes a lot of people to do it, and it's massively expensive, but it's totally worth it because it's upgradable and customizable at any point of time. I mean, you can add and remove a few components and try to scale it up. Obviously, a very few entities in the world can afford to spend this way, because it requires a lot of and you actually require physics experts, you require material engineering experts, you require electrical experts, electronics experts, and obviously the computing experts, so to to build anything that's working. So essentially, quantum computing, when somebody is building their own quantum computer, they are looking at a team size of anywhere between 20 to 100 people. So that's a minimum team size that they should be looking at. So that's how massively complex and expensive it is. So what do we really understand from this is, while a lot of us wouldn't really need to know what is the quantum hardware behind some of the services which are running like IBM, we a knowledge about these tools will help us later when we procure or when our universities procure quantum computer, or let's say an organization where we work actually procures a quantum computer. So how do we really leverage them? So to leverage them, the knowledge of hardware actually helps us, because you can relate to where the errors are coming from, why the errors are so high or probably so low, and probably some of the nitty-gritties that come along, and see how well we can design, or you can take the maximum efficiency out of it. So that's the idea behind knowing the hardware. So, moving on to the next slide. So, this is our first part towards quantum computing. We are going to talk about quantum annealing versus gates approach. Any questions till now, or any particular input? Okay. So, uh, when we say quantum annealing, so it's actually it follows the concept of the physics concept of particles choosing the lower energy state. And when we talk about lower energy state, it's very obvious that and any particle that gets excited obviously will choose to come to a lower state, but it doesn't come back to the lower state immediately. There are certain jitters. There are certain mini excitations that can also happen. There is also external noise that can come in, the thermal energy or the electromagnetic radiation that it absorbs. So there are so many factors which can excite a particle, and it can go to the interim state until it comes down to the ground state. So in quantum annealing, what we are talking about, the computing approach is basically to be able to map the particle behavior and to find a global minimum. So when a particle actually takes the natural path of going into a ground state, which is also relatable to something where we want to find the global minimum, and take traveling salesman for example, which is a classical optimization problem, right? So we have heuristic approaches to solve the traveling salesman problem. Now, if you look at what is the core objective function, the core objective function is essentially to find the shortest path, or shortest cost. I mean, if let's say each path has got a cost, and we have to arrive at a least expensive path rather than the least or the shortest path, we could model even that. Now, in all that, what we're trying to do is we are trying to find a global minimum, and the current approaches are essentially to find the local minimum, which can be the most minimum that we can find in a space, and probably apply the heuristic methods and find out if we are having the minimum value, and we assume that's the best answer. But that may or may not be the case, and there has been a quest to always find the absolute global minimum for a lot of functions, and there are much more complex problems like protein folding or drug discovery, so on and so forth, which actually are far more complex, and they internally break down into a number of objective functions, and each objective function we will have to find a global minimum. So that is where the computing power becomes really, really critical, because we need to really understand it completely. We need to have absolute global minimum, which is not essentially possible in a classical computer unless you have access to supercomputers, and then you run the model for like days and weeks, and then you arrive at a solution. Whereas in quantum computer, it's going to be much, much, much faster. And how does it really do is, and we are taking only the quantum annealing approach right now. We'll talk about the gates approach later. when we say quantum annealing, we start with essentially a quantum mechanical superposition. So you understand that you are translating the state into a matrix, and you are essentially mapping them, and you are finding for all the candidate states in the matrix, you assign the equal weights. And then what you do is each of them, states, you are mapping it to the quantum superpositions, and you then start processing. So what is the processing here? Effectively, processing here is where you are exciting the particular quantum state, and you are trying to find you actually, what you do is you you have this interim Hamiltonian state. You have adiabatic process, and when you actually have the simulation in a computer, you can actually see the waveforms when you can have a jump, and you can see this particular jump in the you see the quantum tunneling which is happening in the between the particles. So when you have the quantum tunneling, you have you have the classical path where you have interim jumps, and then you have eventually you come at a solution. Now this quantum tunneling, your typical classical part takes time, because obviously the particles don't really come to a ground state so easily. There are external excitations, and if you'll have to cool down the temperature, you will have to create an ideal situation, and then eventually the particle will come down to its natural state. And whereas in a adiabatic evolution, what you do is you apply excitations in such a way that you have this traversal, and the transverse is actually controlled in such a way that you bring out the you control it. I mean, you control how the transverse field is applied to the quantum mechanical amplitudes, and the probability to change the amplitude for all the states in parallel is what makes quantum computers so powerful, because it with one transverse field application, what you do is you are able to change the state of all the states in the model. So you are acting upon all the states, which means you are acting upon all the possible values. You are in one step, you are essentially going from state A to state B. Now when you are going from state A to state B, you are actually solving the problem, because your state B is your end state and your state A is your starting state. You have started with equal weights, and then you are processing all of them together, and you are jumping to the end state. Now this end state doesn't come, obviously, if you look at the actual working, you will see the adiabatic evolution doesn't really come very naturally. It doesn't happen so quickly. It follows this particular quantum fluctuations, and the quantum fluctuations is something that doesn't happen so straightforward. It has interim states too. The only difference here, you will find that it's much shorter. It's much faster to be able to arrive at that solution, if you can see where the mouse is. So if you see the state, it actually comes down to your target state pretty quickly, and it's able to come at a solution very quick. Whereas what we are seeing here is the tunnel effect that you see between the states, and where it's following the energy states. It's actually taking time. Whereas out here, when you're applying the quantum fluctuations, you are able to come to that state very quickly. This the rate is actually accelerated, and the Ising model ground state that we arrive to is actually your solution. That is actually your ground state, or the target state that we are talking about in the solution. So when you apply the transverse field and apply basically the quantum fluctuations, you are actually controlling how the transverse field applies to the particle, and then you are able to see that it quickly radiates into the ground state. Now we can start wondering if I'm talking only about a particular category of problem, and I'm talking only about a particular category of problem. We are talking only about optimization problem. We are talking only about a problem that can be solved using optimization techniques. So not all the computationally difficult problems can be classified as optimization problems, because not everything falls in that category. There are far too many computationally intensive, like Shor's gate, for example, Shor's algorithm, for example. So those do not fall under optimization problems, and the optimization problems typically are something like protein folding or computational fluid CFD. So the fluid dynamics, if you want to understand, if there is a modeling for a car that is being done. So typically, automotive industry uses supercomputers to be, to model the CFD, and even with that, what they do is there is a certain level of heuristics that they apply. So talking from a automotive industry, because I have advised to one of the automotive companies for solving some of their problems. So out there, I understood that they do apply a lot of heuristics, and there is a lot of assumptions about an automobile that goes into the design, and that is where the heuristics are inherently applied. And that is where the problem statement reduces, and hence they are able to do it in a supercomputer. But if they were to do it in an absolute what I can say, equation-based approach for all of their behavior. So they will have to arrive at an equation which will run for like years and years. So a quantum computer can actually help them, because some of those equations are actually optimization problems. So they want to find the minimum. So they want to find a minimum drag. They want to find a minimum coefficient, and they probably, if a tire company wants to model how the dynamics occur for different surfaces on which it would run, so they would obviously map it to the friction coefficients. And friction coefficient, you want to have a sweet spot. Again, you cannot have you don't go for a global minimum for a friction, but you want to go to that sweet spot where there is enough friction, but it's not too high, but it's not too low. So you try to arrive at that best. So supercomputers are very good at solving those problems, or even some of the classical approaches with certain assumptions are also doable. They are the classical fit for the quantum annealing, and those are some of the typical customers of D-Wave. I will talk about D-Wave, why I'm talking about them very frequently. So what are the other two-thirds of the problem? The two-thirds of the problem, if you see, are falling into the category of quantum gates, which is a generic computing. So as with the classical computers, we do have certain gates which are available, and like poly gates or C naught and all. So we have a bunch of gates, and the gates itself can be represented as a matrix, because inherently the gates are made up of qubits, and qubits are represented as matrices. So each gate has got its own matrix, and the gates enable the computing. The gate approach actually helped companies like IBM, because it's generic, and like classical computer, IBM has been doing a wonderful job with quantum computers also, and they have understood that gates approach actually helps them model a wider range of problems, and like Shor's algorithm, integer factors. That's a very common thing. In fact, if you come across certain instances where people want to test their first quantum computer, and they know that they have taken a gates approach and they have built a gate driven supercomputer. So the one of the first things that they do is try to run the Shor's algorithm. That's kind of industry standard to see if it really solves. The gate approach has got its own problems, and there are variety of things that need to be taken care, and you will see that we need to tackle each of them differently. So the gate approach is evolving still. It's There is no quantum supremacy with any gate approach quantum computers. Everybody have been talking about quantum supremacy, but we are not yet there. There are certain research applications uh, which have gone into saying that, oh, they have achieved they have bit so and so computers, or they have been able to beat certain records, but generic broad based quantum supremacy is still a little bit away. Quantum annealing has been the go to for the companies like D-Wave for past 10 years, but still they are able to only solve a certain set of problems, and they have that's why they haven't really called themselves to be having quantum supremacy per se. But definitely they have done a brilliant job of bringing a lot of focus onto this industry. This is very much like what Tesla did for electric cars, right? I mean, they have brought a lot of focus to a commercially viable product. And even if they are solving, D-Wave is able to solve about 30% of the problems, computationally difficult problems. They are still able to cover that, and that kind of brought a lot of investment to this quantum computing. If we had talked about quantum computing maybe 10 years ago, we wouldn't have talked much about it, because obviously there was no major discussion about it outside the research circles. There was the companies were not really investing so much, except for maybe one or two companies. Not many were investing, and even for them it was not a serious investment. But fast forward to 2021, we have a lot of computers, and some of the research actually helped in doing those quick turnaround to be able to do that. So in 2011, what happened was, there was an interesting thing. The Ising spin glass system, that research actually came out, and that was the first time that somebody was able to show that quantum annealing machine can be built using this. And D-Wave actually did it, and in that year, in the month of May or June, I don't remember very well. So they actually came up with a beautiful quantum annealing machine. While it was not a great stuff at that time, I mean, even though it was from a research point of view, it was a breakthrough, but from a commercial perspective, it was still not as good as what it is today. So in these 10 years, they have phenomenally improved, and they have been able to bring out, like, 1,000+ qubit machines. In fact, I heard the last that they have brought out is somewhere close to about 5,000. So that's a phenomenal achievement, but which means that we are closer to commercial breakthrough, and we are closer to take it out from the labs and being able to let the companies leverage it. So that these are the two approaches that we will be talking about. And any questions here? Okay. So let's quickly move on, and we are going to talk about the basis of qubits. So the physical basis of qubit, and how do we differentiate them. So you must have I'm assuming you must have learnt about the bracket notation yesterday. That's usually the introduction part of gates and the logic circuits and all. So I'm presuming you are aware of that. So the physical basis, you could be talking about photons, so light based. And when we are talking about photon, obviously we don't talk about a natural source, because natural source have a lot of diffusion. They have varying frequencies. So we usually talk about lasers, where we are able to do it at a single frequency, and we are able to have a very precise control over each of the photons and detect them, because detecting is actually much more difficult in in quantum computing. To be able to detect the output, measure the output state, or rather capture the output state, and being able to translate into a quantum computer, and sorry, a classical computer understandable value, is actually a challenge, because you need elaborate circuitry out there. And that's where photon is also one of the options. So when you are applying light to qubits building, so you are essentially having either you can take a polarization approach, or you can use the photon count to be able to represent the states, or you can look at the phase, and the time at which they are arriving. And while each of them have its own challenges, have its own advantages, have its own way of implementations, we have to understand that photon per se is controlling a laser based equipment. The optic equipments are actually well known. It's not too difficult to set up an optic based instrumentation. It's actually, probably, if you see semiconductor, we'll be talking about little about the semiconductors later. So a semiconductor based or a photon based approach is actually much stable, and less what you can say, susceptible to interference than other approaches. And you can also have electrons or neutron, nucleus, the neutrons being able to give that the neutrality. And you have electrons, where you have only the electron spin, or the the charge that is being measured. And you can then represent them into either a 0 or 1. One of the interesting things that we need to understand in this approach is that uh, the electron spin based approach are extremely difficult, and controlling the electron spin, or measuring them, or the nuclear spin approaches, we talk about all these, we find that they require much more you know colder temperatures. But even within them, electron spin based approach is actually slightly more manageable than the nuclear approach. But then you have the typical NMR that can be used to do model each of the qubits. But then it's a very difficult. I mean, when you say an NMR, nuclear magnetic resonance approach, now that is actually much more difficult to construct, and more expensive, and very difficult to maintain the state. As against electron spin. But even electron spin based approach is not easy. We are going to talk about it a little later in the Transmon approach. And if you look at the other approaches, you will find that we are talking about optical lattices, we are talking about Josephson junction, and we're talking about quantum dots. Will actually talk about address all these points. And these are some of the approaches which are popular today, because these are much more, what we can say, replicable. And these are easy to control. The elaborate setup that is required for one qubit is scalable, in a sense that adding additional qubits doesn't add the entire overhead by itself. I mean, there's a whole setup that you need to do for a photon based. What you need to do is, if you have to measure a single photon and you have to do it for a qubit, you will have to replicate it for an entire second set of qubits. Now the interesting part about a photon based approach is that you cannot, you do not get photons interacting with each other. I mean, they do not really, except for the phase interactions, or when there is an interference that happens when you're crossing the paths. Apart from that, they do not actually interact with each other. So that's one of the problems. So when you are replicating a qubit, you have to actually replicate the entire setup. You have to replicate the mirrors, you will have to replicate the laser guns, you will have to replicate the receivers, you will have to have all those equipments to be able to insulate the photons from external noise, and you have to maintain that absolute environment. Whereas when we are talking about optical lattices, we will see that diamond is being used in one of the approaches, and replicating a diamond is not very difficult. I mean, you just place the diamonds, and you can either apply a microwave or a photon-based approach. And with a microwave approach, it's much easier to replicate, and you know that these particles do interfere with each other or interact with each other much better than a photon, and hence you are able to leverage the setup in such a way that you are able to get a multi-state expression of a gate using a bunch of qubits. And when you are able to build a multi qubit gate, and you are able to express them as a single gate towards your computational field, you are able to naturally replicate it and build a working quantum computer. So that's why you'll see that optical lattices or a Josephson junction or a quantum dot are actually kind of getting more favored. Any questions here? Okay. I'll quickly move on to the next slide. So if you see, there are two different.
Hello, sir. Hello, sir.
Yeah, tell me.
Sir, I have a question on the previous slide.
Sure, tell me.
That you have mentioned that horizontal polarization and vertical polarizations are complex conjugate to each other.
Mm-hmm.
Horizontal polarization and vertical polarization are complex conjugate to each other.
So if you have looked at the polarization and you have looked at the expression and the Bloch sphere, if you map them to the Bloch sphere, you can understand that your horizontal polarization, you can represent it to a bra, and vertical to a ket, and or the 0-1 states, if you are to simplify it. So that's a polarization that we are talking about, and this is we are talking purely from an expression of the states, 0 and 1 state. We are not talking about the superimposition. We are not talking about entanglement here. We are only talking about an expression of 0 and a 1.
No, sir. You told that horizontal polarization representing bra and vertical polarization representing ket. And in fact, bra and ket are complex conjugate to each other. And once they will multiply each other, it will give the your scalar quantity. But in horizontal polarization and vertical polarization, don't give you the scalar quantity.
So that is exactly where we are talking about, right? So the moment you measure, so that's a fundamental, right? I mean, the moment you measure.
No, but see, sir, horizontal polarization and vertical polarization are two representation of polarization. They are not complementary to each other. But how you are mentioning this?
No. That we are talking about measurement of these states. We are talking about the measurement of these states, right?
No, sir. You have mentioned that in the photon that horizontal polarization is one state and vertical polarization is other state, and you have mentioning there one is bra and another is ket.
Correct.
But bra is in one space and ket is in other space. If ket is in one vector space, then bra will be complex conjugate of its vector space. Hence, they are not in the same space. Then how can you say that like this?
No. When you are talking about they are in different space. So when we are talking about them in a different space, we are talking about the measurement, right? So you cannot have them interact with each other once you have measured. So once you have measured, you have the output, right? So once you have the polarization, and once you have observed it, okay, once you have observed, you that state is final, right?
No, sir. No, sir. My question is that any photon can be represented as the linear combination of horizontal polarization and vertical polarization.
Correct.
If you are representing horizontal polarization as bra and vertical polarization as gate, then how can you make it linear combination of this? Your fundamental representation of quantum computing will be violated here.
Okay. So So what we are talking about is a representation. So when you are talking about a representation before the quantum computing is done, obviously when you are talking about two different spaces, horizontal or a vertical polarization, and that is when you will not be able to perform any quantum operation on it. You will not be able to perform any quantum operation on it because you have already observed it. You have already observed the polarization. I mean, you already have observed what is the outcome. When you have already observed...
No. Sir, you have not saying anything about the measurement here. You are just representing. You are representing horizontal polarization as bra and vertical polarization as Kate. But you see, Kate and bra are two different things. If you go the Dirac bracket notation, the representation of bra and representation Kate is different. You can see any quantum mechanics book like your any book, fundamental book, they are totally different. The concept is totally different.
Sure, I get your point. Okay, so maybe how do I put it? If I have to put it this way, right? I mean, if I have to represent them, okay, if I represent them, then they cannot interact. Your summarization is that if I'm representing... Okay, am I audible? Okay, so if I'm representing a bra and a kit, then obviously they cannot interact, is what you are suggesting, and which is true. Which if they are operating in a horizontal or a vertical polarization, you cannot operate on them. Yes, you cannot. But this is after you observe. Okay, I am talking about your states. You're talking about representation of the state. When you are talking about the representation of the state, we are talking about the horizontal and the vertical polarization. And we cannot see, if you have two different polarization, obviously they cannot interact at all. They definitely cannot interact. That's a whole point of quantum computing. And let me do one thing. I will bring up one. Let me bring up another slide.
Sir, one point, if you want to explore. Suppose you are representing horizontal polarization as 0 Kate and vertical polarization as 1 Kate. That is fine. But you are representing 0 Kate 1 polarization and 0 Kate 0 bra in another polarization. It is different thing, sir. As per the basic quantum mechanics is concerned.
No. You are talking about the computation side of things. I am talking about the measurement side of things, where you are measuring the outputs. Okay, so if you have to measure the output, say if I have to represent my output representation, right? Then what do I do? How do I measure? So if I have an output in the same polarization, right? How do I measure them? Right? How do I measure if I have in the same polarization and my measurement, the output measurement, equipments, instruments? How will they identify if I'm purely operating on the polarization? Then how do I measure them? If everything is horizontal, if everything is vertical,
then in order to measure it, I have to use the photon detector so that I can know whether it is horizontal polarization or vertical polarization.
Correct. Correct. That is how they are identified. So when I'm talking about the right side, I'm talking about the measurement side of things. How do I represent them?
Okay, sir. Go ahead.
Yeah. Okay, what we will do is I'll share my email ID. What we'll do is I'll share you the reference and how do I represent this. It's a fairly short session right now to be able to go into detail of this, but definitely there is you have a very perfect point that on the computing side we do not have that, but we are talking about the measurement side, because even in classical computers, so for the easier analogy of understanding, I will talk about the classical computer where we have the state of 0 and 1. So in a state of 0 and 1 we have voltages. So we have an voltage, let's say below 0.7 volts.
But see, sir, 0 is the opposite of 1 as in classical computation. But in quantum computation, horizontal polarization is not opposite of vertical polarization.
Correct. That's perfectly correct. But if I'm representing 0 and 1 purely by their polarization, I mean, from a measurement perspective, and if I have instruments that can measure only the polarization, then how do I end up with? So there is an elaborate circuitry to it. I'll come to that circuitry in a while. So I will come to that particular point.
Okay, sir.
Yeah. Just give me a moment. I'll grab some water.
Okay.
Yeah. Okay. Okay. So qubits can be derived from two different sources. One of them is solid state and the other being a non-solid state. Now, obviously, when we say solid state, we are talking about the superconductor Transmon, and this is a very popular qubit approach. There are various materials which are being used, but all of them require extreme isolation. When you're talking about isolation, it could be electromagnetic, it could be temperature, thermal isolation. So there are various isolations that are required for this. And there is another approach called as nitrogen vacancies center qubits, which uses diamonds, and and there is a reason for using diamonds, and this can also additionally help in quantum communication. I mean, it has a dual role of, it can help in dual role of both compute and communication. So we'll touch upon that point. The semiconductor quantum dots is another solid state, and which is very similar to the classical FET that we have in the classical computers, right? So in a classical computer, in a classical gate, we have a typical MOSFET that are getting there is a lithography, etching process, evaporation, and so on. So we have a similar approach for creating something. What is a quantum dot? Quantum dot is having a similar set of steps: lithography, evaporation, and adding the quantum dot, so on and so forth. And it's actually much more, what I can say, a standard process to create a quantum dot, because the semiconductor production line is a very well-known production line. And the production line is very well known, and it's much easier to be able to replicate, and you have the whole setup ready. Whereas in a superconductor approach or a nitrogen vacancy center qubit approach, today we do not have a production assembly line that can scale, even though we are not there yet. But very soon we will start facing the shortages in superconductor Transmon, and obviously diamonds are not pretty easy to come by. There are a lot of diamonds that would be required, the small diamonds that would be required, very small ones, which undergoes a process. So of all these three things, the scalable one is in terms of production is a semiconductor, whereas in terms of the popularity of qubit is a superconductor. There's a particular reason to this, because we have fundamentally learned that it's all about measuring is all about two-level systems. So if we are talking about electron spin, obviously, when we encode the qubit into the charge state and we want to measure them, so they obviously are sensitive to the charge noise. So it kind of is not in favor with a lot of people, but where you can actually represent qubit. And actually you can handle the states, the charge states, in such a way that even if you have multiple excitation states for an electron, you can map them to two different states. So that's kind of debatable, and there are quite a few challenges out there, but the challenges have been overcome. We will talk about those challenges a little in detail later, and we'll focus on the Transmon Qubit for a simple reason, because a large number of implementations are actually done in Transmon Qubit. So we'll definitely talk about it a little more, and we'll also talk about the semiconductor and the NB approach here. Okay. Why we are classifying them as a solid state? Because we are purely acting on the state of the material. We are talking about the material which are available, and they are in their solid state. We do not really require a non-solid to be done, and a non-solid is obviously a difficult one to control in an environment. Obviously, you need a little more special care when you're talking about anything which is not a solid. So in data centers, obviously, you need solid state devices. If we have to go to the non-solid state, we'll talk about the photon derived qubit. So we leverage the polarization, and we'll be using them for both compute and interconnects, and basically we are talking about computation, communication, and the computation. And this is more favored as against the trapped ion, which is another non-solid state, for a simple fact that you can control optics, you have a better optic equipment, instrumentation, and so optics is much better in terms of that. But you'll already understand that the photonics based quantum computing is very well demonstrated, but there are certain challenges to it. So the challenges are that you can do it under two different sampling models. So you can take either a boson sampling model or a KLM sampling model for the quantum computing, and you can map solving a problem to either of these models. We'll talk about, there is a whole research to the boson and the KLM model, and we will find that boson is actually limited in terms of the applicability. Not every problem statement can be modeled into a qubit which can follow a boson model. And so obviously the number of applications that are available for under this model is very limited. Whereas in KLM, obviously we have two different problems out there. One is definitely the general problem of it not being available as a generic, what we can say, the KLM protocol is not, it cannot be linearly, scaled. It needs much more non-linear scaling, and so if you start adding qubits, and if you start adding optical elements to it, and you start going ahead with scaling the qubits, so you will have to have much more interconnects. So there will be more interconnects. So for one interconnect, you will have two equipments, and when you're talking about 3 qubits, you will have 8 interconnects, and so on and so forth. So This is one of the problems that we face with the KLM protocol, and there are obviously methods to overcome them, and there is the computing resources. The basically, when we say the computing resources, we are talking about the measurement side, where we are talking about how do we capture the outcome of the computing, and we are able to translate it into usable data. So when we are talking about that, then obviously there are certain heuristic methods to be able to figure out how do we reduce them, or how do we reuse them. But doing it at a scale and doing it at that kind of granular level for each of the qubit, it becomes very cumbersome, and that's why there are practical challenges with the KLM approach. So the boson sampling model for the for the method is I mean it has been fairly recent research. It's not very old research, but it has been only applied to boson sampling problems, so it has not been applied to a lot of other problems. And it follows. I mean, it has both exact and approximate sampling. And in a quantum computing, we would want to go for an exact sampling, and that kind of limits in how much we can do, because when we are talking about these sampling problems, there is. I will share the whole research paper, and you'll find that while photonics is actually an emerging approach. In fact, there is a company called as Photonic, which actually builds quantum computing onto the silicon. So they are able to bring it to the silicon, and they are able to bring those processes. But we still find that a lot of challenges exist in these, and not all the problems can be solved. Similar to the D-Wave, again, photonics is focusing on a subset of problem solving. And your optic based approach is again very limited in terms of how we can solve the problems. And if we talk about the trapped ion method, trapped ion definitely is not scalable in terms of and it's not production. What I can say, it cannot be used in a commercially production environment, because very simple that if you have an ion to be managed, then it's definitely not a solid state. And something which is not a solid state, you have to manage the ions, and you'll have to manage them, and you have to get the ions to be able to first transport into your into your measurement units, your compute unit. Basically, we are having a circuitry which is going to excite them, and which is then going to trap them. And I mean, the excitation is obviously with a laser. So the laser equipment per se is not very large, because just the laser, it's not about measurement part, it's only about the excitation. So laser to use as an excitation is fairly standard. It's a compact device, but to be able to record the output, that is where the challenge is, because you will need those high-speed camera setups, or the quantum level camera setup, the ones that can take about 1 million shots a second or 1 trillion shots a second. So those kind of setup that we are talking about, and it's fairly expensive, and it's also not scalable, because they actually are huge, and if you have to do it for thousands of qubits, obviously it's not scalable. You will need a whole building to probably set up these things. So it's not really scalable that way. And so that's why we are talking about more about photonics in a non-solid state. So if we compare all these methods, you will find that the Transmon approach is actually the most common, followed by the the photonics approach. And there is also semiconductor. We talked about the quantum dot approach. Definitely it has, but it requires much more temperature control and electromagnetic shielding than the other approaches, and that is why it's kind of a little complicated. But it's the wafer per se is very compact, and so that is easily transportable, and so that's why it is being used in some of the research quantum computers. But in terms of production quantum computers, we still are a bit away for that. Any questions here? Okay. Okay. So we are coming to one of the main topics of the Transmon qubits. Transmon qubits is leveraging superconductors. We saw that before, and we will have to find out what a transmon qubit is. So a transmon qubit basically is a transmission line shunted plasma oscillation. So what it does is it leverages anharmonic oscillation. So if you look at this graph, so what was happening is each of the states is having exactly the same delta. For each of the states, so energy states that we are talking about. So each of them is having their own, you have a uniform differences. When we are talking about an anharmonic oscillator, we are talking about states which are where the energy differences in the higher states are much lesser, and where an additional little bit of energy will take it to the next excitation state. So that kind of makes it a slightly flatter and wider wave, and this is important because it's actually forming the cornerstone of excitation and measurement. And microwaves are usually used for the excitation because they are very stable and controllable, because you have standard microwave setups available, and microwave setups is also very tiny. I mean, you can, what I can say, shrink a microwave excitation. What you can say, the spear. So you can actually control, direct the microwaves in a very small area, and you can actually excite a small qubit. So it's much more controllable, and it's not and you do not have to expose the whole material for the entire microwave. It also depends on how much you are able to expose the material to the excitation state. And obviously you do not want the nearby the junction, Josephson junction, to get impacted by this. So Josephson junction, they are segregated in different or they are segregated in such a way that you do not have a very close ones, and you are not placing them so close that they start interfering with each other, but you want them to interact only in a very controlled way, and you control them using microwaves for excitation. And so when you're taking them to the higher energy state, the transitions become less pronounced, and what you have is you do not have so much of state jumps as much as you would see in other states, and so you are able to abstract them together into one state. So anything which is not my zero state can be considered as an one state. So mapping these multiple states into energy states into one state and operate upon them. And on the measurement, it is extremely critical, and this is where a lot of problems lie. How do you measure them? Because the energy is so short-lived, and it can quickly fall out of that, and that's why you would want to measure the energy state. And for that there are various approaches available, and where you convert the energy states and you map them to electrical voltage, and you have a specific reference voltages which you can map them to a 0 or a 1. And once you do that, you are able to consume it outside the quantum computer. So mapping these transitions and doing this anharmonic transition or oscillation is actually very critical. And this is where we talk about the controlling of the energy. And the challenge is that what typically happens is that you're operating a microwave usually in the range of 4 to 5 gigahertz, which is a very common approach taken by a lot of researchers, because microwave, obviously you can scale it anywhere from 300 400 megahertz to hundreds of gigahertz, but then people typically work in the 4 to 5 gigahertz because it's much, you have equipments, standard equipments, you have materials which can respond to that. There are stable materials, you do not have unwanted behavior beyond this, and this particular frequency is good enough to get a stable oscillation. It's good enough to get compute out of it, but it also requires that it has a challenge that it requires a lot of equipments to keep it under low temperatures. And when we are talking about low temperature, we are talking about in millikelvin, so which is like just above zero. So there are, obviously there have been a lot of research in last couple of years. If you see, there have been a lot of research in terms of how, superconducting transmons can be done even at a higher temperatures. The only problem is how long can it survive in continuous operation. That's a question, because usually there tend to be leakages when you're talking about slightly higher temperatures, and when you're talking about temperatures which are in 3-4 Kelvin, then obviously the leakages are much more prominent, and thermal leakages then will kind of shut down it will cause a runaway. And once the runaway happens, then your excitation states go for a toss, and all the quantum effect that you are talking about will just simply vanish. You'll not have any of those effects that you want to work with. You will not have those oscillations. You will not in a controlled way, and hence the thermal shielding is critical. Obviously, the lower you go, it is much more difficult to control. But at the higher ones, what happens is on a continuous operation, the thermal runaway tends to be more pronounced. And it's a common concern for all the equipments. And when we are talking about the temperature control, we have to understand that we have to have a superconducting, not just the transmon material per se by itself. We also need superconductors to be able to transport those oscillations out, and also be able to translate and take it to a classical computer. And classical computers typically cannot operate, and your standard instrumentation cannot work under such a low temperature. So obviously they will also have their own effects. So what you do is you have superconducting cables which you connect to the transmon substrate, and you actually take it back to the equipment where you are able to bring all the qubit operation outputs into that interface, and where you can translate them according to the voltages, and then you can take it out as compute outcome. So out here there are few of the concepts where you need to have a coherence. So you similar to light, if you are talking about the excitation states of an energy in a particle in a superconductor, we have coherence. So when we have a coherence, obviously when you have a coherence, obviously you cannot do a quantum computing. So what you need to have is the initial state must be dephased. So in order to be able to excite them, and in order to perform the gate operation and bring them back to its initial state and then repeat. Because in quantum computing, it's very important that you cannot store the state. You cannot store the state of any material. You cannot store. The moment you store, you are actually losing out on the quantum benefits. The superimposition is lost. The moment you are observing, you are losing on its ability. So one of the important factors is to be able to oscillate between the initial state, which is a dephased state, and also in the gate state, where where you are actually having the values. So the first thing is when we want qubits to be dephased, we want to be in a computable phase. We want to have we want to make sure that they do not have they are not in coherence. So there is a particular challenge associated to it when we are building a gate. I'll come to it in a moment. So why this is important? Because when a phase is undefined, that is exactly what we talk about as a qubit initial state. It's a pure state, and you cannot really measure the state. Because when you measure the state, obviously you are losing on it because you are making it coherent, and when you are measuring, you are making it coherent, and then there is a dealing with dephasing again. Okay. One of the important parts out here is also to understand that we will have to take it, so we will have to, if I'll have to refer the diagram below, when having a superconducting qubit. So we have a resonator, an XY drive, and a flux bias, and so on. So what we are doing here is we are subjecting the Transmon Qubit, okay, and so we are having the induction, and we are essentially tuning it to a frequency so that we are able to get what I can say, distinct states, distinct 0 and 1 state. If I have to show it here, so if I have to plan it here as I do have a representation here. So if I am talking this as a 0 and 1 state, what I'm doing here is I am taking this as a 0 state, and anything beyond I'm taking it as a 1 state. Okay, but I do not want them to go. Okay, I'm sorry about that. So I do not want them to go beyond to a different state, because if I'm going to a different state, I'm obviously losing out on the effect of computing. So we want the state to be held for as long as possible. So this state that we want them to be as long as possible, but the excitation, right? We want them to happen in a very short time, so that it's able to quickly arrive at the target state. And if it's 0, it's 0, there is no change, then there is obviously there's no change. But the target state is important for us. How long we are able to stay in the target state is essential. Now if we have to get this, there are 3 challenges here. One challenge is that how quickly we are able to arrive at a target state. 2 is how long we are able to hold it in the target state. And 3, when we start defacing, how quickly all the qubits become defaced. Because one of the major problems with the materials is they do not deface instantly. They do not deface all together. It's not that you apply it and all the qubits that you have in a gate, they all come to the same state, original state, computable state again. You are not able to do that quickly. So these are 3 different challenges, and obviously the presence of a capacitor is very critical here. And if you see, the capacitor plays a large role in how it gets defaced, and how it how long the charge is held. And we will see that we will need to operate in typically 4 to 5 gigahertz. Google has actually done this for 4 to 8 gigahertz range. They have tried it out in a vast range of frequencies. And the problems, obviously, I have told, we need to bring it down to close to absolute 0 as possible. And this kind of temperatures are extremely difficult to sustain. So that's where we also need to understand that what is the What is the excitation energy? What is the how much frequency we need to apply to be able to arrive at the excitation phase? So how well we are able to how much frequency we need to apply? So typically Google at least have done this is again from a Google experiment, and this is in the range of 150 to 350 megahertz. So if you look at this particular frequency, so this is the sweet spot that they arrived. Why this is the sweet spot? Because when we are talking about the defacing, we will talk about the defacing first, because I want the qubit to come back to my to my initial state faster so that I can repeat it. So you have charge noise when you have similar to a photon. You have interference in this also, where you have charge noise for the electrons. And if you have a charge noise, then obviously you will need more capacitance to be able to reduce that effect. So you have a much more flatter charge noise. So that's how you have the standard electronics. And the large capacitance also means that you cannot quickly ramp up from one state to another. So you cannot have that gate time. So your gate time becomes larger if you do not have the faster gate time. So obviously that also takes time. Whereas we want that to be fast for a simple reason that we want everything to be coming together and at the same time. Otherwise, we will typically have taking a long time, and the fundamental of going to a quantum computer is lost. If we are not able to figure the target state in let's say of a few microseconds, so then obviously there is no point in doing a quantum computer, because your supercomputer are capable if you have to do it in milliseconds or probably in seconds. So that is why we want them. The most beautiful part is how the charge holds, and this is where a larger capacitance also helps us, because it helps us to keep the state, the target state for a longer duration before it can start defacing. Now that is where we have a control over the input circuitry, and we are able to tune the frequency. And with this particular sweet spot, Google has been able to get 10 to 15 nanosecond the gate timing, and they are able to get something in the range of 50 to 100 microseconds for dephasing. So you essentially see that in about 200 odd microseconds they are done with the whole operation. Now, 200 microseconds in an enterprise world is actually large, because 200 microseconds is large for any operation. So what do we achieve out of this? That is why we need computationally difficult problems only in the quantum computing. So a lot of people tend to think that, okay, we have everything, quantum does faster, so dump everything to quantum computer. No, that doesn't work, because every operation that you do is going to take about 200 milliseconds, and these are physical limits. I mean, there is no electronic tuning that you can do to this. Obviously there are certain tuning that you can do, but beyond a point there are limits of physics, so you cannot go beyond that. And when you come to a very short pulse, we will talk about the pulse control also. When we are talking about the pulse, then you have those outliers in the pulse. There is a excitation state and a de-excitation activity. So when these things are happening, even the pulse which kind of cuts off your pulse shaping, which kind of cuts off your outliers. So we have a limitation in terms of how much we can do, how narrow we can get to the pulse shaping. So obviously there are limitations in terms of how quickly the quantum computer can respond. And if your individual qubits cannot respond in under let's say 100 microseconds, then how can you translate that into a gate? Because obviously the gate will compute in the same time, but when you're taking to the next level above the gate, where you're modeling your problems into gates and you are modeling these gates into qubits, if the gate themselves are going to respond in hundreds of microseconds, then obviously your original problem cannot be solved in under few seconds. So if that is the case, then the original problem might as well be solved by a supercomputer than with a quantum computer. And that's why to get how quickly we are able to change the states and we are able to come at an initial state is critical. Now, if you look at the classical problems, the supercomputers versus a quantum computer, it's a very, very common debate these days. The quantum computers, everybody says, oh yeah, it is great and all, but the actual implementation experts who actually sit down, they have this dilemma all the while. So can we map every problem to a quantum computer? No. Can we map every problem to a supercomputer? Yes. Classical supercomputer? Yes, we can. Should we do it? Probably no, because supercomputers they are expensive to run, and they also take a lot of time to compute. And in some of the cases, they will take like forever, like 10,000 years to compute, and that's not a feasible thing. Whereas a quantum computer would be able to achieve that in a single step. This is the beauty of quantum computer, and that is where your charge time and decharge, your dephasing time are essential. When we are talking about having this pulse, we have to have something called as a pulse shaping. So obviously the electronics experts out there can tell me better about what are the different pulse shaping techniques, but at least the common ones tend to be either Gaussian or cosine wave approach, because what happens is a rectangular doesn't get very useful because you have those side lobes and which keep coming around, and which are then you'll have to have a cutoff for the amplitude, and you will have to figure out and then once again you will have to have a processing electronics and then amplify the output again. So there is a whole lot of electronic circuitry again that you need to do, and this is for each qubit that we are talking about. So to do this, what we can do is we can go for a Gaussian, because it tends to quickly give me one single pulse, and it's also not have those lobes again. So the lobes are very, very tiny, if at all they are existing in practical scenario. In an absolute world, yes, there is just one Gaussian, but then again it extends to infinity. So you cannot have the pulse shaping in a good way. The other challenge with cosine is it's somewhere in between your the rectangular and the Gaussian shaping, and the cosine is actually a sweet spot. If you are able to tune the cosine pulse shaping circuitry in a way that you are able to extract that pulse in the duration that you want, but your side lobes are also less, that is completely doable. Now, in this approach, what happens is it's a single state approach. I mean, you have a single order equation that you are applying to the pulse shaping. So, in a practical scenario, what tends to happen, you go for a second order, and second order, pulse shaping is done. Some people have tried, different, pulse shaping, but eventually a second order, pulse shaping with a cosine, kind of is good enough. And we are talking about error rates also here, because when you have side lobes, when you have those outliers, when you have those leakage currents from your standard electronics, which is also going to create some interference. So measuring the output out here is very critical, and there are certain error rates out here, and that is why you will see certain errors being introduced here also in the output state also. And Google engineers, at least what they did was they created their own CMOS chipset. In fact, they did it sometime last year. They came out with a chipset, and they were able to demonstrate last year that they kind of ended up having their own waveform generator for this, because the standard waveform generator requires a lot of cabling. So each qubit requires let's say about 12 odd bits. It has got more additional pins, and then you have a lot of circuitry. You need to send a lot of data, because you need to operate it at a very high frequency. If you're talking about 4 to 5 gigahertz of operation for your excitation phase, your pulse shaping should be able to operate at least at at reasonable speed, depending on the electronic circuitry. Obviously the frequency would be tuned, but if you're talking about that, then obviously the rate of input the control signals. So that would be very high. Standard DAC, which is shown here. So you will see that this is for 1 qubit. You are actually having 5 DACs, sorry, 6 DACs and 2 ADCs. So when you are talking about this, then obviously you have so many controllers, and you have so much of data to be done for just for 1 qubit. And if you have to put in 16 lines for each, and if you're talking about 8, so then obviously you're having 144 lines for every qubit. And if we are talking about thousands of, at least 1,000 qubit computer, we are talking about so many odd lines just for this. And then you have additional circuitry, then you have the controllers, then you have the output measurement amplifiers, then you have so on and so forth. So obviously the kind of circuitry becomes very complex, and there are error rates everywhere. Even your standard DAC chip that you buy from any of the leading providers, even you talk about a space grade equipment, even then you will find that there is a certain level of errors which is going to creep up. And so coming up with something like a 4% error rate, Google engineers have done a phenomenal job at that. They have put this into an entire CMOS circuit. They have not done a great job at being able to remove the common components and able to keep it compact. Definitely they can do it more compact, but from POC perspective, they were able to fabricate a chip which can perform this entire control operation. So if your control operations are so your basic qubit, which is your inductors and so on. So if you are able to control the output, the control circuitry is one chip. So one chip is now controlling 1 qubit. So if you have to have 1,000 qubit, you need to have 1,000 chip. And if you are having 1,000 chip, the power consumption is high. When you're having power consumption of so many chips, obviously the heat dissipation, the thermal dissipation is definitely going to be there. And when we are talking about the millikelvin temperature, we obviously are looking at the standard operating temperature, which is like the room temperature, which is about 300 odd Kelvin. So we know that it's not easy to control. So then it can the more thermal dissipation it does, there is no perfect insulator anywhere. So there is always going to be minor fluctuations in your core qubit temperature. And if your core qubit temperature is going to change, then obviously your qubit is gone for a toss. So this is where the external circuitry is critical. And the qubit we are able to control using a chip. And the challenge out here is, again, how do you handle the voltage which is available at the output of the qubit? I spoke about it before also. And you will see that when we're talking about the readout here, we know that the temperature, the voltage that we are getting is so low, because you see the attenuation is so much that eventually the loss that we have is so much that we usually end up with a voltage of about microvolts, or just about under a millivolt kind of a scenario. So if we are having that level of voltages which is available, to be able to convert them, because if it's a weak current, it's not too difficult. But then if the voltages are low, to be able to differentiate between the states and be able to get a stable output here becomes a challenge. So these are some of the things that they have overcome, and it's not that people have not done it. It's just that the kind of circuitry that we require to do this is much more complex. This is the origin of these are the various origins of the errors that we are talking about, and eventually translates to the reason why we run so many loops. So we usually run a 10,000 loop or a 100 loop or a 1,000 loop, depending on the problem statement that we are doing, and we get a range or a probabilistic outcome, and we take the most probabilistic outcome as a readout value for our classical computer, and upon this we can further process the data. Then it becomes data, pure data, which classical computers can ingest. Any questions here? Okay. We'll then go to the nitrogen vacuum center. So this is actually a very what I can say is unique. Like I said before, it can be used for both compute and communication. The reason is the way the diamond structure is. The diamond structure is very stable and it's hard, and it also has unique properties in the sense that it's pure carbon, because you don't get pure carbons so much, and pure carbon like pure silicon is great stuff for doing computations. And they obviously, with all the valency, and we know that physics and chemistry behind it, so we have that the diamond. And what we do is we remove one carbon atom from one of the lattices, and what we then do is we introduce nitrogen. Now the nitrogen, what it does is, obviously nitrogen being 14, and you have certain carbon 12 and carbon 13 atoms. So even diamond has got carbon 12 and carbon 13, which is why you will find that there are certain challenges in NV center also. So carbon 12 is very stable, and when you introduce in a pure carbon 12 environment, if you introduce nitrogen, then you will get exactly one electron spin, which is additional electron which is available to measure the spin and apply the operations on the NV center. The problem is the challenge with this approach is that you have what we call the carbon 13, and about 1 to 2% of carbons that we find in a diamond, in a typical diamond, sometimes it is less, sometimes it's more, is usually carbon 13. And when you have carbon 13, obviously it's going to impact the electron spin of the nitrogen. The advantage that we get out here is the electron spin is available for compute, and it can be excited by either a microwave or an optic, which is a photon. And the other point here is that you also are able to transmit this photon out. And the out here again, the phase that we talk about, the polarization we talked about earlier. Now again, since this whole photon is available, it's also available for communication. You can as well, you might be able to communicate between two different qubits. You have one diamond, one qubit, and you have another diamond, another qubit. If there is a photon which is getting emitted from one qubit and which is available for another qubit to be able to consume, then obviously you are establishing a communication between them. And if you are able to establish a communication between them, you could as well, and light, obviously, when we have, and these are typically lasers, when we have them, we have standard equipments which can transfer it with great fidelity. We can transfer it to very long distances. So essentially, you're talking about transferring it from one lab to another. People have demonstrated, I think it was in Germany or somewhere in Europe, I do not recall exactly. So what they did was, they were using NV Center. They had demonstrated, between two labs, So they were about 2 odd kilometers away, and they were able to transfer this photon, and they were able to establish quantum communication. Now, this quantum communication at this distance is like an achievement. China obviously did it, I believe, about a couple of years ago. They had established and they had shown it that they are able to do, communication with their satellite also. Now that's another ball game, but we understand that there's a lot of research going on out here, and when NV Center is able to do this dual rule where you can do a compute and you are also able to transmit a photon, communicate, it becomes very practical, in a sense that we are able to use it to do both the things together. And like a classical computer, you are in the same unit, you are able to do a compute and you are able to communicate. And because of this, it's able to interconnect with the higher layers of abstraction. So they are able to easily connect. And again, for all reasons, we do have microwave spin manipulation being a preferred approach, because as I spoke earlier, the microwave is much more controllable over a very tiny surface, and the diamonds that we are talking about, the diamond NV Center we are talking about, are too tiny for typical usage, and they are extremely tiny. So you'd probably be able to procure them for about maybe 100 rupees for a diamond. And even artificially lab prepared diamonds are good enough, because fundamentally they are carbon, and artificially grown diamonds are much better to control, because you can insert the substrate at any time. Now there are questions around how do we get nitrogen center within the diamond. Obviously there are standard annealing and radiation process, and a lot of different particles have been tried. So some people have used protons, some people have used electrons. So you have standard gamma guns and electron guns which can do this job, and these are extremely precision driven, and they can actually knock off one single carbon atom from an NV center, which can be simply placed in a cavity, and this cavity can be used. And if it's an optical cavity, obviously you use it for optical manipulation, and if you are using a microwave cavity, then you can use it for a microwave manipulation. And you place it and you have a single tiny diamond having a single qubit, which is completely doable. With the standard equipment that we have, we do not need additional equipments for it, which is a great stuff, because being able to produce, and I spoke of this before, I mean, being able to produce like quantum dot, it's very important that we have a production line which is able to supply your nitrogen or your substrates for computation, which is essential in the sense that you have now a nitrogen vacancy center, and you have absolutely a single nitrogen vacancy. You do not have any interference from anything else, which is great. The only problem here is, as I spoke before, is C13 and the behavior of the C13. So within the diamond, what do we have is we have an interference within them. We do not have an interference from outside, but we have an interference within them. Now, when we are talking about the interference between them, so if I apply the microwave spin, and if there is a nearby carbon-13 atom which is also having a spin, and now that spin would tend to, if it is close enough for interference, obviously it's going to interfere. So my outcome might not be exactly what I wanted. So that's a charge. But the beauty of using the microwave spin manipulation is that they can operate at a very high frequency. I mean, you can have nanosecond response time or a gate timing that you have. So you are able to do it at a high operation. It is stable. because it's a solid state, and you can even operate it at a normal temperature. I mean, there are certain challenges, obviously, with the thermal, impacting them, but even at normal temperatures, you have a fairly long coherence time. So where you have the gate state, right, the coherent state, you are able to read the state out. So you are able to do that, and that's very important, because if you do not have this, if the thermal noise is not going to impact it so easily, then it's a great stuff, because you can build practical computers. But again, the presence of carbon-13 is a challenge. So how it is mitigated? It is mitigated by kind of observing what is the lattice structure and how we can use them and how close they are to interfering them. So there is a certain level of production process where they might probably produce 1,000 diamonds with a NV center, and probably not all of the 1,000 might be used. They might be using a 300 or a 400, because they might deem that some of them might have too much of interference. So that's a kind of operation that happens, and eventually that's scalable. From a production perspective, that is scalable, and from an NV center, the electron spin, again, we will have the microwave states that we are applying, and we measure the electron spin with a standard ones, which is similar to Transmon units, but you have a lot different circuitry though. You have you once again measure them, and you are able to arrive at the output here. Now, important parts that we are talking about here is NV center, how they can be connected. So if you are having photon based excitation, then you can also have the photons talk to another qubits. But if you are applying the microwave, then how do you do it? So there are you take out that readout value, and what you do is you also couple them with other qubits if they are independent qubits. If you have to operate them as a gate, then obviously you will have to interconnect them, and this interconnection is where electromagnetic shielding is required. We spoke about the electromagnetic shielding, and since we are talking about low voltage, and we are talking about the very finely tuned microwave, and it's operating on a fairly narrow band. It's not operating at a very broad band. So you have 150, 200, 300 megahertz if you're talking about. Then obviously it's fairly a small band when you're talking about the actual operation band at 300 at gigahertz. So definitely we need to shield them, and we need to ensure that there is enough energy, there is enough fidelity in the signal. And when we have enough fidelity in the signal, we are able to communicate between both the qubits. And definitely there is a latency between the qubits of there is a certain level of latency, but this latency, when you start operating them together, and when you are able to get them, so we are talking about the initial state latency, which is few nanoseconds. So we are talking about how quickly it can ramp up, and we are able to achieve the quantum state. Okay, so how does it all bind together to a higher order computation? So you have we are talking about a NOT gate, and if I have to come back to the gates, let me quickly come back to the gates. Okay, if I have to come back to let's say a CNOT gate, so it's a fairly complex one. So when we and if you are taking a TOEFL, of course it's fairly complex because you have many qubits which have to be put together into a single gate, and when you are operating them at a single gate, the challenge here is also that you will have to have the system producing the output in the same way. So your probabilistic outcome is now going to be slightly more diverse, which means that a very sharp 99% probabilistic outcome is not something that you will find all the time. You will find certain level of probabilistic outcome where you will have less than 99% and probably even lesser, and that's exactly where the next level of chips come into play, where they are able to assess. So that's a next level of control electronics that sit around each of the gates. Now, once you have constructed a gate, if you have to have something which is something which is going to sit around your control and control each of the gates, then this control circuitry also generates a lot of data, because they are able to know what is the error rates that are coming out. The latest thing, I don't recollect the company's name. I do not exactly recollect. So there is a computer cube control, I believe, or a control cube. I don't recollect the name exactly, but what they do is they give controller equipments for quantum computers. And what this controller equipments do is they are able to capture all this information and all this data, sensor level data, your voltage readouts. So all this information are now available, and there are algorithms that they have applied on top of it, machine learning algorithms that they have applied on top of it, and they basis of the machine learning outcome, they automatically tune these controllers, which in turn tune the qubit microprocessors. I mean, we saw that Google guys were doing one chip for one qubit, and there are people who have done individual controllers for each qubit, and so there are different ADCs and DACs. So these can be controlled by that control queue equipment, and that control queue equipment is actually automatically tuned by itself using machine learning. So that's a next level of abstraction, where your classical computer is now driving your behavior of the gates, or ensuring that the gates are giving you the highest possible outcome. So then how does it tie back into my classical problem? Then once you have the gates, you have the standard way of breaking down your problem into the gates, and you give it your your quantum control circuits are working its way, and you see that what are the voltage values, and you are mapping them to the values, and you have the standard readouts. So yeah, so this is all about where we have any questions. We have I think about 5 minutes.
Okay, sir. I have a question.
Sure.
You are talking about quantum machine learning, but the problem we want to solve is basically the classical problem, because
correct.
Okay. Now the point is that how the classical problem is fit to the quantum model, because in order to make it fit, you have to create a quantum state, and as per the quantum mechanics knowledge is concerned, you cannot create a quantum state, because a state can neither be created nor be destroyed.
Perfect.
Then how can you do it?
Correct. So what you do is, and this is exactly why we spoke that the initial state in the Transmon Qubit, right? We spoke of the initial state where you should not be knowing, it should be in a dephased or a decoherent state. You cannot have coherence in your, initial state. And that is where, you have to understand that you cannot directly map a problem to a state directly. You cannot do that directly. You have to translate the first, you have to create an objective function. You have to create matrix representation for it. Once you create a matrix representation for it, you are then able to build a gates. You are able to build a gate circuitry, right? And which I believe some of your other speakers will be talking about. So the gate circuitry is basically you put together a gate to represent a particular matrix. When you are able to represent gates to a particular matrix, and now what you do is you are now executing only the gates, And gates internally are translated into qubits. And obviously, we spoke about how the qubits form together. I mean, we haven't gone into detail of how the qubits interact together to form a gate, but we know that there are qubits can interact with each other either through photon or this. So that's how you translate.
Hello, sir. My point is that, so, see, in any computational model, you have to provide the input for the computations.
Correct.
Now, the machine is quantum machine and our input is classical. Then how we feed the classical input into the quantum computing? That is my point.
Correct. So that is where there's a difference in the thought process. So the difference in the thought process is...
No, we are not going to the thought process. We are going to how to input the classical input to the quantum computing. That is my point.
Correct. So, so that is where the matrix algebra comes in. Okay. So
see, it is mathematical form, but how we will input the? I think you are not getting my question.
So you are talking about the physical states, right? I mean, how do I?
How? Okay.
Yeah. So for me, in a classical computer, if I have a chip, I give voltage as 0, and then I get, then I have an output pin where I get 0 or a 1. I mean, you're talking about the
no. I am talking about data part. Suppose you are suppose for an example, you want to do the image classification. Then in that case, image is in the binary form 0, 1 you are representing, and you are inputting in the classical computer, and you are getting the output according to the algorithm. My point is that if once you are using quantum computer, you have the classical information. Then how can you feed to the quantum computing? Because quantum computing does not know about classical information. They don't know about 0 and 1. They know only about 0 ket and 1 ket. That means you're then how can we input the information in classical to quantum? How the transition will be taken place in that manner?
Okay, let me take you through a journey in the reverse direction. Okay, so we know that there are gates. Okay, we are taking a gate-based approach here. Because it's a generic computing that we are talking about. So I'm taking a gate-based approach. So if I have to go by the gate-based approach, so what do I do is I go through. I have all these gates available. I have shown you that there are each of the gates that are represented against by a matrix, right? So each of the gates now. How do you in if I have to go into electronics, right? Classical computers, electronics, because obviously there is an input, there is an output. Correct? There is an input, there is an output. Okay, in a classical computer. If you're talking about that individually, in a classical computer, within a chip, you have gates, and you have gates which obviously it's not one transistor alone. So yeah, you understand that again. It's a bunch of transistors that work together. When you're talking about an AND gate, or you're talking about a NOR gate, an XOR gate, so you have transistors working together. Similarly, out here you have qubits working together as gates. You have gates which are available, which can perform operations. So if you go through a simple poly gate, right? A poly gate is actually the simplest of all, or probably if you're going for a tougher, I'm not going to go for it because it's a bit complex. There are more elements to it. So we are talking about a poly gate. A poly gate is standard. You have 4 elements within the matrix, and when you are representing them as a matrix, you are doing matrix multiplication. When you are doing a matrix multiplication, what you are doing? You are putting the gates together to arrive at an outcome. Correct? In a classical computer, how do you achieve it? If you have to do a matrix computation, how do you achieve? If you have a target state, you know what are your target states. I know that this is my operation.
Sir, I think you did not get my question. Leave the question.
Okay, I'll do one thing because I'm trying to explain in the other direction where you have the gates, your building blocks of a quantum computer. When you're trying to solve a problem, you have to think in terms of gates. If you start thinking in terms of quantum states, what happens is you are trying to map the input and the output. But that doesn't happen out there, because once you have a gate, you start implementing modeling in a gate. Okay, I'll actually share you. There is a whole nice article about how do you translate a problem from a higher order problem to a gate level, and this expression is what is going to help you solve the problem. And when you come to a gate level, then underlying implementation. Today, if I have to give you an example, IBM actually uses Transmon behind in their online Qiskit that they are offering, so interface that they are offering. In the background, they are having a supercomputer, a superconducting Transmon Qubit driven computer. So what they have is they have this already in place. What they have abstracted out is they have abstracted the way the gates are utilized. What you are currently doing is in your problem, if you go, and I'm sure you have the Qiskit, this one, some, where you have the inputs and where you have the outputs, right? Where you are modeling your problem. When you model the problem, you have the expression in Qiskit, and when you are doing it, you are expressing it in the gates. When you are rendering, you will find an output. Now, this output is not something which is coming out of nowhere. There is a certain state, and what it does is it maps the target state, and it gives you the outcome as per the target state. Now, this is how it is. In the lack of
sir, have you gone through the Qiskit programming provided by the?
Yes. I will share you that. I will share you that link where.
No. I have written many Qiskit programming in my project.
So let's do one thing.
Gone through this.
So let's do one thing. Maybe we can connect offline after this, because I know that 11 o'clock is your next session.
Okay,
so
sir.
What we will do is we will connect after this, and I will explain you why I'm saying what I'm saying. And we'll definitely, and I completely agree your point. I mean, coming from a classical world, I know that there are certain things which people assume that, okay, I have an input, I have an output, but my quantum computer doesn't have an input. I mean, you cannot define a state there. So how do we get an output? We will talk about it.
Okay.
Yeah.
Okay.
Sure. Thanks. My email ID and phone number would be available. Manesh sir, you might be having that. So if you can share with whoever is interested, I can definitely. I would love to connect with them.
Yes, thank you, Karthik Commissioner sir, for giving your valuable time to us from your busy schedule.
Thank you.
Hope our esteemed participants have learned a lot from you, sir.
Thank you so much.
Tomorrow we have another session with you, sir. Hope to meet you again tomorrow. So Thank you once again, sir.
Thank you. Thanks a lot.